If you want to share a screen, I'll introduce you and we can start.
Yes, with pleasure. Let me just first put it on the full screen. Give me one more minute because I had it open in the wrong program, which doesn't allow full screen. Just keep chatting. Everything is ready. We just need 1 minute. Well, is it that I always have to do all the chatting in this group?
Actually, if you don't mind repeating some of the chatting, I was changing my headphones when you said that you may be in Toronto, but I missed the continuation of the sentence. So you're coming to Toronto soon?
Not that soon, but there is this special semester organized by Microsoft next year. Yes, so okay. I hope to participate in that.
All right.
Well, thank you for your enthusiastic answer.
Great.
Now, what is this? This is not the right kind of view I want to have on this. I don't quite understand. Sorry, I have had some problems with my computer, so things are a little bit slow these days.
Well, who doesn't?
Indeed. There, that looks great. Now I'm going to share it, and then as soon as I escape from it, it goes out of the full screen. So I think I'm going to share it anyway, and then I will put it on the full screen manually. That's the best thing.
Okay. Yeah, we can see.
Great. So now you can see, and now let me try to go back to it and put it in the full screen. This looks better, right? Just now we have to go back to the beginning. Okay, so this is the beginning, and I hope it doesn't start moving on its own. Spencer, I'm all
okay,
there.
Great. It's my pleasure to introduce Mirna Dzamonja, who will talk about reasonable infinite structures and Morass-generic structures.
Thank you very much. So, people, we haven't seen each other for a while, so some of you have kept in touch, some of you not. So I will take just a few minutes to say my affiliation, because I moved to Paris finally after so many years that I was sharing my life between England and Paris, and now I am in IRIF, which is a CNRS based research unit at the Université. I have a typo here. It should be Université deParis, which is the same university as our friends Boban and Stevo and Alessandro, but in a different research group. My research group is in what here in France goes under theoretical computer science, and I think everywhere else in the world goes under mathematics. Well, so anyway, so that's where I am now, and I'm supported by a grant that I got, which is called From Finite to Infinite. And what I'm going to tell you about is a part of that grant. It's a small part. I mean, it's part of the program of that grant. It's a small part. And if we have time at the end, we might add some things that are not on the slides, but are present in my thinking. So what's the idea of this? Well, the title is supposed to indicate that we are going from the finite to the infinite. And of course, we are not the first ones. I'm not the first one to think of this. The idea is that we want to study the passage from properties of the finite to the infinite. So properties of finite to infinite structures. And the idea that interests us is a transfer of certain properties. What might we mean by this? Well, let me just say a few things that people have been studying. One is small, big Ramsey degrees. So you have some class of finite structures. You know that the finite structures have small empty degrees, small finite, small empty degrees. You build a big structure somehow out of them. And then you wonder if this big structure has small, big Ramsey degrees. So this has been done very successfully by people studying Frese constructions. And in recent times, I've been working with Dana Bartoshova, Limsko, and Rehanna Patel on a theorem that applies this to ultra-product structures, so pseudo-finite structures. Another context that this kind of thinking has appeared are graph theoretic invariants. So this was started by the work of Lovash and his group. A book about that is his 2006 book on graphones. So the idea there is that you also have something which looks like a pseudo-finite structure, but in fact it is not just a pseudo-finite structure of graphs, but also of the verb measure on them. And in a limit, you get a continuous function from the square of the unit interval to the unit interval, which represents in many ways the sequence of graphs that you have started from. And in particular, many graph theoretic invariants can somehow carry to this measurable function, which is called a graph. Then one might study various logical properties. Certainly people doing alpha products in the 50s have studied this type of question, although not always so much centered on finite versus the infinite, but mostly small versus large in the cardinal sense. So we have the famous Bosch theorem. And then something that the audience here perhaps will know a little bit less is that in the algorithmics community, people study this quite a lot, actually. And what they are interested in is what they call small infinite sets. So what are small infinite sets? So these are some structures. They might be first order structures, might be structures in some other logic that are built out of finite in a very nice way, or they are somehow connected with the finite. For example, a very nice class studied by Bojanček in his book on small infinite sets. The structures that only have finitely many orbits of the automorphism group. So these are some examples. So my project that is not the one that I have just mentioned, but another project that I'm
sorry, can I ask a question?
Yes.
About what you said last. I don't see why is it the smallness property. I mean, you can have a set as large as you want, which has no structure at all, and there is only one orbit for automorphism.
Yes,
group.
yes, so, in that they are not interested in the size. They're really interested in the number of orbits. So
also small is a misnomer, really. Okay.
Exactly, yes. So the word small can be understood in different ways, but they're only interested in countable structures in their work so far. Well, so this work that I have learned by, talking to people in this type of computer science has inspired me also to take another look into a favorite cardinal in this community, or at least to me, Aleph 1. Well, as we know, there is a big difference between countable infinite and the first uncountable infinite. Basically, everything fails. Everything that we know, like Ramsey theorem or a compactness theorem, many things that we know about Aleph 0 fail at Aleph 1. And one thing that has occupied the set theoretic community is to try to develop descriptive set theory on the space 2 to the omega 1 or similarly defined spaces. So to have some sort of generalized descriptive set theory at the cardinal Aleph 1. And this has had some very nice results, but also some very unexpected failures of generalizations of what we know about the bare space, and many surprising negative results about this available in the literature. So a project that I have in mind is to actually try to study effectiveness on Aleph-1 by associating effectiveness not to the way that we do it in classical descriptive set theory, but to some sort of automata. And this actually connects to what I have been just telling you, because if you want to build an automata associated to this automaton is kind of a small object. So this whole theory of small infinite sets came from a particular kind of automata that are called data automata. So this is a project that might or might not work, but this is something that's also in the back of my mind during the work that I'm going to present to you. But we are not going to talk about this in this talk. So what is this? What is actually new in this approach that we have been seeing in many different contexts is actually a big difference, in my opinion, between what people have tried in the past and what people are trying now. So in the past, the finite and the infinite were sort of studied mostly by trying to reflect something that you know about one of those contexts to the other context. So a positive thing to do, which works well, is to build, to bring to the finite back from the infinite if we have some sort of compactness property. So we can prove the finite Ramsey theorem from the infinite one and so forth. But in the other direction, in general, it's quite hard to say something about the infinite, even if you know much about the finite. I think that Erdos and company have some jokes about that, that the infinite they do straight away and the finite takes more time or something like that. So just the point is that not that many things carry over in the full completeness of these contexts. And well, here is another event from Canada. There was this very nice conference in 1991 where, you know, the long time where many of you perhaps were not yet born, but this is a very nice conference that was held. I wasn't yet mathematically born either. So I wasn't present at the conference, but the book has many nice papers. And well, the conclusion is that not that many things carry over. Well, so what can we contribute to this is to take another view into this process, actually, not to just look into the size of the things, but to look at how the infinite object was built from the finite ones. So this is really this procedure of building that interests us. So in a sense, we are going against Cantor here. Cantor made a big news by talking about the actual infinity, when for centuries before him, people were only looking at the potential infinity, which was kind of the limit of finite numbers. Well, so in this sense, we are going against this idea of Cantor because we are also interested in looking into some sort of limits. So rather than looking at all infinite structures in some class, we want to look at the structures that are built out of finite structures in some specific way. And then the limit will have that property. Well, you have, of course, seen this. There is nobody in this audience who hasn't seen the beautiful work of Fraser structures that our community has been producing. But I mentioned some other structures, graphones, and then graphings is another kind of a limit. First order convergence. This is well, it is also based on graphones, but it takes into account also the case of sparse graphs. Morasses, which will be the object that we will talk about today. Ultra products, which is probably an object that's familiar to everybody here. So these are different kinds of limits, and the experience shows that it seems to be worthwhile studying what one can obtain as the limit of such structures in some sort of classifying way. So we'll concentrate on morasses, and let me tell you why and what these objects are. So the morasses that interest us are give us a specific way to build objects of size Aleph1 using finite approximations. So at first, this looks sort of controversial because it looks like we are skipping a cardinal, and that's actually the whole point of Morass, that we are building an object through finite approximations. Now, if you know forcing, you have certainly seen this, building objects of size Aleph1 through finite approximations, but the point of morasses is that they exist actually just as EFC. Let me say that there is a very efficient way of building objects on size Aleph1. There are many, but I think the most familiar one probably is through Todorcevic's method of walks on ordinals. Since I am interested very much in this part of the construction, which says that we are going through finite approximations, I prefer in this particular work to work with morasses, but probably an equivalent theory can be obtained by somehow translating through the Todorcevic's method. I don't know. So let me say that the work on morasses is joint work with Wiesław Kubisz in Prague. So after I left England, I was for a few months employed in Prague in the context of a large project that Wiesław has on Fresnel limits. So his point of view is classification of Fresnel limits, and he has also obtained many concrete results by looking on these Fresnel limits, not only for first order logic, but many other contexts. Well, so he's interested in this type of context, building from finite structures. And so in this work, we have tried to understand these Morass-based structures in a way that he has studied Fresnel limits. So let me say what a Morass is. The story starts in 1972, a long time ago, in the famous paper of Jensen. He studied two cardinal transfer principles in L. I don't know if everybody knows what the two cardinal transfer principle is, so let me just tell you. It's a little bit like an elementary submodel. So, you know, an elementary submodel is you take a structure of size kappa and you want to find a submodel of size, let's say lambda, where lambda is smaller than kappa. And in first order logic, you can do this type of things using Lowenheim's column theorems. But what if you actually work in a different logic and you want to set up a unary predicate, a special unary predicate in your structure? So it's like working in monadic second order logic. So the Lowenheim's column theorem doesn't apply. And so what you want to do is to look at transfer principles between a structure of size kappa where the special unary predicate has size kappa prime, and transferring that to a structure of size lambda where the unary predicate has size lambda prime. So that's the question that he studied for many possible cardinals, and he obtained many nice results about this in L. And the tool that he used were morasses. So what are the morasses? In morasses, there are hence two cardinals that comes from the two cardinal transfer principle, but basically they are combinatorial structures whose purpose is to build objects of say size kappa plus n for some n, so n times plus, but we use small approximations of size less than kappa. And this type of object would be called kappa n Morass. So this says that approximations are from size less than kappa go to kappa plus n. Well, for some reason, the finite approximations Yeah, so no, this fits, sorry, just forget the last sentence I said. So we will be interested in omega-1 morasses, which means the morasses that use finite pieces and build an object of size omega plus, which is omega-1. Now I must confess that morasses are very complicated type of animal, and very few people actually understand what they are like. And in spite of the wonderful work that Jensen has done about them, there has been relatively little work done on morasses. The two people who have worked a lot on morasses are Dan Velleman, who is my brother by Kuhnen, so a fellow student of Kuhnen, although many years before me, and another person who is my close co-worker for many years, Charles Morgan. So in this talk, we will be talking about Velleman's contribution. So what Velleman did is to use a vastly simplified framework. So it was in his PhD thesis in 1984. He defined an alternative object called the simplified morass, and he proved that such a morass exists if and only if Jensen's morass exists. And this is really the object that interests us and that the object that has appeared in applications. And the point is that for the pair omega-1, such an object actually exists in ZFC. So let me just say that one of the first applications of this method was by Velleman himself, who proved that he reproved Schellach's theorem, which says that after adding one coin real to a universe of set theory, one obtains a Suslin tree. These days, people tend to show this theorem by using Todorciewicz's method. Okay, so let me show you what's a neat. I will just actually skip these words later, neat simplified omega-1 morass. I will just call this a morass. So it's a system. And this is at this point that we are missing a blackboard, because I would like to show you this system. But let me go through the definition very slowly, so perhaps that you can make some notes for yourself and imagine this object. So imagine these theta alphas as some sort of steps that are getting longer and longer. So these are lines that are put one on top of each other, and theta alpha for alpha less than omega is just a finite structure, finite set, and theta omega is omega-1. So these thetas are building up to omega-1. These are the finite sets that build up to omega-1. And between these thetas, there is a system of functions. And the whole trick of this is you have certainly seen many kind of projective limits, like people use in topology or in Boolean algebras, where you have one kind of projection. Well, here it is something similar. So this F alpha beta, you might think as some sort of push up of theta alpha to theta beta, except that it is not unique. So there are several functions possible in this F alpha beta. So these are some ways to push theta alpha up to theta beta. And now what are the basic properties of these? So the first property I have already described. Theta alpha is a finite number, a positive number, and theta omega is omega-1. And the functions in F alpha beta are sets which are order preserving. So you see, we are thinking of theta alphas as ordinals, and of course theta omega is an ordinal, and we want to preserve the order. And we are going from theta alpha to theta beta. And for the last one, omega, if we go from F alpha to omega, then we also obtain a set of order preserving functions from theta alpha to omega-1, so that when you look at the images of all the functions in the system, these images cover omega-1. So we have lots of functions, and we cover omega-1 every time for each alpha. And what is the connection between these systems? Is that they commute very nicely. So if you take 3 of those steps, alpha, beta, and gamma, which are all finite, when you look at the functions from alpha to gamma that are in your family F alpha gamma, you can actually factorize them as compositions of functions that are going from alpha to beta, so they're in the family F alpha beta, and the functions that are going from beta to gamma. So there is this decomposition. And now what happens is that at successor stages, we certainly always contain the identity function, and either this is all, or we have just 2 functions. So this is a big simplification introduced by Velleman. There are just 2 functions in F alpha alpha plus 1. The identity, there are at most 2, the identity, and some H alpha, which looks like the identity up to some point, let us call it beta, which is an element of theta alpha. So up to this beta, we have just the identity. And then we throw beta far away. We throw beta larger than theta alpha. This is an important thing in proving theorems about these things. And then we have some sort of, let us say, amalgamation here. So whenever we have beta 0 and beta 1 that are finite, and we take 2 functions, first one goes from beta 0 to omega, and the other one goes from beta 1 to omega, we can actually compose them somehow. We can amalgamate them in the sense that we can find a larger ordinal gamma and a common function g from omega to gamma, such that the functions and functions from beta L to gamma, or beta 0 and beta 1, such that FL is actually obtained as going first from beta to gamma by F alpha prime, and this G, and this works for both L equals 0 and L equal to 1. So in some sense, this G is an amalgam of a sort of these functions. So that's all. These are the properties. And an interesting thing again is that such a thing exists just in ZFC. Now let me tell you what we're going to do with such a thing. Okay, so we have this and so on. So what we are interested in is preserving, putting some structure on those theta alpha for a finite alpha, and then pushing that structure on omega 1 by this system of functions. Imagine a simple example, a graph. Okay, so you have on each theta alpha some graph, and of course you want these graphs to cohere with the functions. So you want the functions to preserve the edge and the non-edge relation, or just to preserve edge, whatever you want to study. Let's say they are, the model theoretic embeddings, they preserve both the edge and the non-edge relation. And now you wonder what kind of graph you're going to get on omega 1 by defining in omega 1, you define that 2 points are connected if they are images of 2 functions, let us say f1 and f2, for some f1 and f2, that agree. Well, in fact, let me take this back. So two points are connected if there exists an alpha, and an f in f alpha omega, such that these 2 points are images of 2 connected points in theta alpha. And because of all these properties of agreement and amalgamation, we have that this is actually a well-defined definition. So you can now play with this object and define orders and any kind of other kind of structure that you may want by inducing the structure on the big object omega 1 through these functions and the structure on these finite sets. So it is kind of a limit process. So let's see. So that's what we mean by objects built along such a Morass. So let us fix let's say we are in some universe of set theory B, and we fix a Morass M, then we may consider what happens in V. We may also consider what happens in the forcing extensions on V. Let me say that this type of constructions has been studied in the context of adding one coin real. I mentioned already the result of Velleman, in which he proved Sherlock's result on adding a Suslin tree. It turns out that there is a theory already about how this type of constructions reacts when you add a coin real. So the idea in that context is you have what I have just told you. You induce the structure on omega 1 by the finite structures. All of that is in V, but you make some decisions according to what the coin real tells you to do. And since you only have omega many things, then you can at every n decide depending on the value n of the coin real, and this type of construction is well understood. It is not understood for any other kind of reals, and so much scope for study in this. So let us look at now this in kind of abstract generality. We look at K and C. These are classes of structures of first order languages. There isn't really a reason to limit ourselves only to first order structures, but I think it is easier to think about it if we do. So let us just talk about first order structures. And what we want actually is to kind of imitate what is known about phrase structures when we know about something about the finite structures that form the phrase structure. So this notation is kind of inspired by that. We look at the class of finite structures, and we have so we have two different classes, and one will be the finite ones and the other one will be the infinite ones. And they are both closed on this isomorphism, and we know what an embedding means in them. So we'll consider this, and we call this a paired class. A paired class is a pair such that C consists of finite structures, K consists of structures of size at most ∝1. And the language of C is a restriction of the language of K. So this is a bit of a generalization of what I've already told you in my example with graphs. We had the same language both for C and K. So C was the finite graphs, K was the graphs of size omega 1. But we might as well allow some other symbols in K. So we might have some things which are not induced by the Morass. And we want, therefore, to, since we might allow this difference, to say how the embeddings in K relate to the embeddings in C. So this is kind of an obvious requirement that if two things embed into each other in the sense of K, then they should also embed in the sense of C once we have restricted to the language of C. And also, if we have a finite structure which happens to be in K, then its restriction to the language of C is in C. So that is the basic context. And of course, in the language of C, we might allow symbols that have large arity and that cannot even be interpreted unless there is a large enough structure. So we always understand that the arity is interpreted only in the structures. The symbols are interpreted only in the structures that have enough space to interpret the arities. Okay, so as I say, this is just a small generalization of the key example of the small example. We have graphs and we build some graph on omega 1. Oops, what did I say? Well, I said these are structures of first order, so there are functions, there are relations. But by usual tricks, you can code the functions into relations. So we can just consider relation symbols. So we'll just think about relational languages. And now we want to look at not just one particular construction using a Morass, but we want to look at the whole class of objects that we can obtain using this method. So we're going to call that MK. So these are objects in the language K that are built along the Morass. So let me give you a formal definition. So these are all structures which I'll call C star, whose domain is omega 1, and which are obtained in the following way. For each alpha less than omega, we are given a structure whose domain is theta alpha, and this structure is in C. And for each alpha less than beta less than omega, the functions from alpha to beta theta in the Morass F alpha beta are actually C embeddings. They preserve the relations. And then the structure on C star is defined so that for each symbol from C, we actually just do exactly the same as I told you that we have done for the graphs. That is, for each alpha less than omega and F in F alpha omega, the function F will be a C embedding from its domain, which is theta alpha, to the range of it, but restricted to L of C. But there may be more stuff in K. But we cannot control K by the Morass. We can just control what happens in C. Well, in many interesting cases, C and K are exactly the same class, but people do ask questions about enlargement of language. I will mention that in a minute. So that's why it's interesting to have the possibility of these two classes. So the first thing that you might wonder, okay, I want to study this object. Does it depend on the Morass that we choose? Because nobody told you that there is a Morass that is unique. So this class might actually depend on which Morass we chose. And well, actually doesn't, in the following sense. If we fix one Morass M, and we have another Morass, let's call it M prime, we define M prime according to this new Morass. So we replace theta alpha by sigma alpha, we replace F alpha beta by G alpha beta. What do we obtain? Well, we obtain that the classes are the same up to isomorphism. What do I mean? The classes are the same up to isomorphism. What I mean is that for every object in M prime K, there is an isomorphic object in MK, and vice versa. For every object in MK, there is an isomorphic object in M prime K. So which Morass we choose does not change anything about this class. So let's see some theorems that one might want to prove. Now, let us look at the case that C is equal to K. So we just look at the Morass limit considered in the same language as the objects in C. Then we can actually see that there is a lot of connection between this and phrase construction, in the sense that we can find a club of delta such that when we look at the intersection of this structure C star to delta, calling that N delta, what we have that the age of that N delta, so all the finite substructures, is a phrase class, and N delta is its phrase element. So these Morasses are kind of sequences of phrase elements. And in fact, we can obtain the age for such delta, we can obtain the age of N delta as the substructure closure of the family M alpha, alpha less than omega, where M alpha is simply the element of C on the level theta alpha. So these M alphas do not form a phrase class because they are not closed under, to start with, they are not a hereditary class. They are not closed undertaking substructures, but if we do take that substructure closure, then indeed we obtain a Frese class. So, so this means this all and deltas are sort of isomorphic to each other. Sort of, they are isomorphic to each other. And taking into account the part 1 of this theorem, we obtain that the model C star is homogeneous. And this is therefore a very nice way to produce examples of homogeneous objects of size Aleph1. As an application, one may think of the constructions of homogeneous graphs of size Aleph1. And there is something, so we played with that a bit. And there is also something from that comes from a class that maybe other people considered as well, but I had learned it from Vyacheslav and his previous work. He considered this idea of antimetric spaces. So antimetric spaces are spaces which are, they are topological spaces which are endowed not with a metric but with an antimetric. So this is a function d from the pairs of the space to the positive real numbers, such that it satisfies exactly the opposite of the triangle inequality. So there is an edge such that its antimetric is greater than the sum of the antimetrics of the two other edges in every triangle. So the anti-triangle inequality, if you want. So they turned up in some examples that Vyacheslav constructed with Frese limits, and the question was left open: if you can have a homogeneous such space of size Aleph1, and actually it is, he showed that it is not possible to have such a space of size larger than C. Well, using this theorem and just putting all finite antimetric spaces on these as the same alphas, we obtain a homogeneous antimetric space of size Aleph1. This also tells you something interesting. I think this example, which is perhaps a toy, tells us something that is in the back of my mind and that of many people these days, is to look at how far you can get on Aleph2 by using finite approximations. So this has famously can come up with the work of Itai Neyman, in which he established a way of forcing with objects of size Aleph2 by what he calls with finite conditions. So these are finite sequences of two types of elementary submodels. But even much before that, specific cases of such forcing constructions were known. I think the first one was the one by Roslanovsky and Shelach, who wrote a paper that not many people, I think, they wrote such a series of papers that was so long that each paper in the series was very long, so that perhaps of this people haven't really read that, but this was in the early 90s. They considered generalizations of proper forcing. And they called this forcing preserving semi-diamonds. And in this work, there is a construction of a club on omega-2 using finite conditions and element. Well, later, a different construction was given by Friedman and Mitchell. And well, then my student, ex-student, Gregor Dolenad and me, we constructed the square. And then, you know, this very beautiful approach of Neyman came up, and later on, Velichkovich, Mohammed Pur, and others, Gitek, Magidor, they all studied this. Okay, so there is a big interest in constructing objects on size of Aleph2 using forcing with finite, something finite in it, finite conditions, or finite whatever you wish. You may ask, well, is there a way to do this just in ZFC? Well, of course, we might be very quick and say, no, this is an intuition, but why not? Well, this simple example here shows that you couldn't hope to have such a generalization of such a Morass construction, at least to size Aleph2, because we know that such an object cannot exist in ZFC. This homogeneous antimetric space cannot exist in ZFC in size Aleph2. So it is structurally impossible to generalize this to a similar context on Aleph2. I actually think that it's very interesting to consider the limitations of this method of constructing things with finite approximations, even by forcing. And there are many combinatorial results that show that these things should stop at Aleph4. Nobody knows even Aleph2, Aleph3 is a complete mystery, but they should somehow stop at Aleph4. So I like to consider this type of limits. Well, it's a small digression, let me go. Let me actually make another digression. You might wonder, well, why would we want to study methods of constructing objects of size Aleph1 when we already know so much about them? Well, my main motivation would be to get out of the negativity. So we have many negative results about Aleph1, which to us who like to play with infinite structures, just say, well, these are negative results, the recherche theorem doesn't hold, whatever. But if you actually like to think about structures as giving you a way to do something on them, so you have the structure, you want to define an automata, some decidability procedure, something, you have this structure which is going to be sort of a base for something else, then you would like to know that this structure has some nice and tame properties. So part of this is to look at tame structures of size Aleph1 and to defend the thesis that if you have a tame structure, then actually the nice combinatorics from Aleph0 does carry to that, whatever tame might mean. So here is this. Here is the heart of why things are different. Well, why does not Ramsey theorem hold at Aleph1? This is a Todorcevic's theorem, a conjecture about what would be Todorcevic's theorem put on steroids. I think many people in Toronto know this problem very well. It's a hard conjecture. It has a very unevocative name, Q of Aleph1. It was discovered by Cardinal and Comiat in 2002. And it says the following thing: for every graph of chromatic number at least Aleph1, with no restriction on the size, there is an edge coloring of this graph into Aleph1 many colors, which is sort of wild. How is it wild? It is wild because if I take now, I fix this C, the edge coloring, and now I look at vertex colorings, and I allow myself Aleph0 many colors, then I will be able to find a class of this vertex coloring, which assumes every value of C. So if you think about this and apply this to the complete graph on Aleph1 vertices, you get exactly the beautiful Todorcevic's theorem about the Ramsey coloring of the pairs of countable ordinals into omega-1 many colors, so that every uncountable subset gets all the colors. So this is actually a specific case of this conjecture. This conjecture is still open in its full generality. And so what does this have to do with tame structures of size Aleph1? Well, if you want to construct a counterexample to such a conjecture, then you might like to consider something that is tame. So perhaps an interesting question, even if it doesn't give directly a counterexample, but just an interesting question to consider is what this conjecture means in the context of these Morass constructions. So that's one thing on our plate, as they say. Let's carry on. So now that we have discovered some of the ambitions, let us go to things that are known about the phrase structures and see if we can, what we can say about the Morass structures. So one thing that people have studied a lot in the context of phrase structures is the aptly called the Ehrenfried phrase game. So what is it? We have two models of the same signature, and we have two players, which living here in the 5th arrondissement of Paris, I certainly should call Abelard and Eloise. I think these names are due to our friend Adrian Matthias. But Abelard and Eloise are actually historical people who are buried in a church, which is now a museum, in the 5th arrondissement of Paris. So they play a game from their graves, Abelard and Eloise. And Abelard chooses an element of the union of A, union B, and Eloise responds by a sort of isomorphic copy. So this means she has to continue a partial isomorphism that we imagine that they have already built. So they building an isomorphism, Abelard gives a challenge, Eloise responds. And at the limit stages, they take unions and then they keep going. So what is known for this game has been studied for countable models since the 1950s. It was invented at that time. It was not a joint paper of Ehrenfried and Frese. These are two separate works proving the same theorems. For countable models, the winning strategy of Eloise in this game describes the first order isomorphism. That is, these two objects A and B are isomorphic if and only if Eloise has a winning strategy. In other lengths of this game, so for larger objects, this only gives elementary equivalence up to some quantifier rank. And for models of size Aleph1, the winning strategy definitely does not describe the full isomorphism. This is a result of Hittinen and Vannanen from 1990s. So how about these tame models that we have built? Here is a little theorem. If A and B are Morass constructions and Eloise has a winning strategy in the game, then A and B are actually isomorphic. So this is an example of a theorem that sort of justifies the thesis that we have here a tame class of models. And I think it give you something more about games. Vyacheslav and Adam Kravchuk studied these abstract Banach-Mazur games. So they defined these games on the class, which they call sigma C, of unions of increasing countable chains of structures in C. So you have these finite models and you look at increasing countable chains on the subsets that's preserving the structure. And you take the unions. So this is a structure and all the structures you get like that, you call sigma C. And what do the players do in this game? Well, they choose an increasing countable sequence of elements of C so that the result is in this sigma C. So sigma C are not all the possible structures. They are some chosen structures and they have to choose so that they end at this. Or there are many versions, or you just take all sigma C and you have a different winning condition. So the winning condition may be being isomorphic to a given model, or being embeddable in a given model, or negations of those. So various winning conditions on these constructions. And they have a very nice paper published on this, quite general paper. So now you can define the same thing with respect to these Morass constructions. So you have two players, they construct a countable sequence of elements of C, but now you don't want them just to increase along the countable unions, you want them to increase along the Morass. And now you can look at the final model. It's a Morass model. It's a Morass limit, so it's an element of this class Nk. And now you can ask, well, when does the good player has a winning strategy? When do the players have a winning strategy? So perhaps some of you know, I've been very interested in the problem of universality and embeddability in my work. So for me, at least, of particular interest is the winning condition of not being embeddable in any of the given models. And why is this actually interesting is specifically not just because it's my taste. Well, because I actually know some theorems that we can prove about non-universality using the Morasses. So there are some theorems, including some of my own, where old theorems, where one can use a Morass that to obtain that in a model by adding one coin real, there is a structure, it might be a graph or an order, a Boolean algebra, which doesn't embed into any such structure in the ground model. So those of you that know about universality probably know that adding omega-2 coin reals kind of destroys all the universality hopes. There are no universal models for anything. There is no universal graph. I'm talking about the size Aleph1. But this type of proofs actually goes through studying what happens when you add one coin real. Or few coin reals. So this you can prove by studying the names in the, you can prove this type of theorems in many ways, but one very nice way of proving them is to look at these Morass constructions and just see what one coin real does when it threads the Morass. So let me illustrate that technique. So I'm going to illustrate the technique by recalling an old proof, which is from a paper of mine, where I was interested to add Banach spaces that somehow do not embed in some sense into any Banach space of a similar kind in the ground model. In fact, of course, the final goal of this type of theorem is to obtain some non-universality result by iterating the coin reals and knowing that in the final model there is no universal. But I think it is equally interesting to see what happens when you add one coin reals. So you will see that from the title that here we are talking about Banach spaces, and before I was talking to you about first order structures. So you might feel that I've been very dishonest here. You know, what is the first order structure going to tell us about Banach spaces, which are certainly not in any sense first order. Well, there is a nice way of constructing a Banach space by going through the steps of representation theorems. So the first you construct a Boolean algebra. So Boolean algebra certainly is a first order object. Then you apply the Stone representation theorem, and out of this Boolean algebra comes out a compact topological space. Then you take the space of continuous functions on that, and that is then a Banach space. So in fact, you construct this Banach space by constructing the algebra and controlling what will happen in these two ways of extensions, if you want, to representations. You can go even further. You can look at then all the measures on this C of, so one more representation that people have used to study measure theory on Banach spaces. Okay, so using this technique, we have shown that by adding one coin real through a Morass, we can add a Boolean algebra of size Aleph1, such that in the extension by one coin real, the Banach space C of the stone space of A is uniformly Gateau renormable. This just means, for those in the know, that the stone space is a uniform Eberlein compact. But if you don't know these words, do not worry. Anyway, it's a nice Banach space, and it does not isomorphically embed into any space X star, which is in the ground model and has density Aleph1. So the fact that the Boolean algebra has size Aleph1 will mean that this space, the Banach space, has density Aleph1. It is very nice in the extension, but yet it cannot be isomorphically embedded into anything that has density Aleph1 and comes from the ground model. So let me just show you how this works to illustrate to you how you can thread a coin reel through a Morass construction. So you define a Boolean algebra as follows. You probably know what I'm going to do, but perhaps there are some small surprises. So you know that we will define this Boolean algebra as a limit, Morass limit of some first order structures. So probably one could do this in many ways, but what I found convenient is to take the language of two binary relation symbols that in our mind are to be interpreted as the order in the Boolean algebra and the disjointness in the Boolean algebra. So we have the else sentence 5. It says that this less or equal star is a partial order, and D is symmetric and anti-reflexive, and that the statements D xy and less or equal star xy are contradictory. So this is basically less or equal star is the order and D is disjointness. And our aim is to obtain a model of this particular sentence. This model will be called I. This model will live on omega 1. And then when we interpret in that model less or equal star as the Boolean less or equal and D as the disjointness, then from this I we can generate a Boolean algebra. So we generate a Boolean algebra A freely except for the relations that are present in I. So actually, I'm not building the Boolean algebra directly. I'm building a set of generators of the Boolean algebra and putting some relations on them that will be helpful for me to achieve this non-embeddability result. So why such a thing exists? Well, it is possible to generate, why is it possible to generate a Boolean algebra from this I? Because of the compactness theorem and the fact that we have defined the sentence so that it is consistent with the axioms of Boolean algebra, of a Boolean algebra. So every finite bit of this task that we have in generating this large Boolean algebra is consistent. So it is everything is consistent, and therefore it has a model of size Aleph1. So that's why we can generate. And how do we control the fact that we want this Banach space to not be embeddable? So the density clearly is, we have density omega 1, and we can prove some positive things like this uniform Gateau renormable. But let's not worry about that. Let's worry about the main point. How do we assure that this space does not embed into anything from the ground model that has density Aleph1? So let's take a candidate like X star, some Banach space from the ground model of density Aleph1. And we enumerate a dense set. So what we want to guarantee is the following, that whenever I have a natural number n star, which is at least 3, and whenever I have a function from omega 1 to omega 1, which I'm going to call J, there will be n star squared i's such that if the norm of the sum of those z's indexed by j's of those i's is small, so less than n star minus 1, then in A, these guys are disjoint. And if the norm is greater or equal than n star minus 1, then these i's are ordered in A. This will simply give us a control on the norm in the space that we have constructed out of this Boolean algebra A. And it will, and this J, you can think of it as, you know, given an embedding, you take J to be the inverse image of the generators. Well, and then you see that this cannot be an embedding because there is a big gap in the norm. That's the idea. So to say this more properly, for any potential embedding T, there is an n star such that for all x, we have this inequality. So this is any embedding will have, this is a basic Vanna space theory. And then it suffices to guarantee that what I told you before, if I have an n star greater or equal than 3, an uncountable subset of omega 1, I have an embedding from A to omega 1 in V, then there are i's in A which exemplify this dichotomy star that we have had in the previous slide. So how can you, okay, so let us just stop for a second to see if we agree that this is the case. This is a sketch of a proof, so it doesn't give you all the details, but I think you can imagine that this is how the work will bring you this contradiction. If you have ever done things with the coin forcing, this is kind of the thing that works. The point of using coin forcing rather than some other forcing is the following. It's a well-known lemma about coin reals. So if you take any natural number k greater or equal than 1, and any j from omega 1 to omega 1 to k in the extension, then you can capture this by a j0 in V such that j0 and j agree on a large set in V. So in other words, first we are interested in the case k equal to 1. If we have some function j from omega 1 to omega 1 in the extension, then we know that this function on a large set, on a set of size A, omega 1 is represented by a ground model function. And so that's why it suffices to guarantee what is written on top of this slide. And then you guarantee that in a sort of inductive way. So one direction of this research is to look what happens when we add, what kind of games we can win by adding some other types of reals. So this proof that I have shown you is a prototype proof to say that in the extension by one coin real, we have a winning strategy in the non-embeddability game. So the guy who wants to be non-embeddable into the ground model objects wins. He can consider that in this way. So now we may ask the same question about other kinds of reals, what kind of games we can obtain. And well, so this is still research in progress, but I hope that I have given you some taste of this. So let me conclude just about this MK. The models here provide rich possibilities of objects of size Aleph1. Yet since they are built out of finite pieces, they are easy to control. So we get some sort of tame objects of size Aleph1. And we obtain that, in fact, they are sort of like an uncountable version of those nice countable models that people study. Many questions are to ask in analogy to Frese constructions. Let me just say one kind of next step in this or sort of parallel project I mentioned about those automata So in automata theory, people, well, the automata were basically introduced by people who were interested in decidability questions. So the person who really put this, the automata existed, but putting them on the map of what logicians studied was a paper of Rabin in 1965, who studied decidability of the monadic second order logic in certain contexts and proved positive theorems by associating this to automata. So he associated this to an automaton that lives on a tree 2 to the less than omega. And this was a breakthrough because before that people only studied finite automata. So his automaton lives on a tree, and then there is a huge theory of automata that live on countable trees and what they decide and so on. But it's always about countable trees. There are Dushi automata, Lider automata, and so on. In my knowledge, nobody has yet studied automata that live on an uncountable tree. Ita Niemann has wrecked building on the wreck of others like Schellach and Lefschetz and others, Gurevich. The monadic second order theory of ordinals, of all ordinals, and has shown some theorems by some positive theorems by associating to a certain type of automata, and some negative theorems. Okay, so there are some questions that one may ask about the monadic second order theory of trees, not just of ordinals, but of trees. And in this context, it is interesting to associate to such trees some automaton which would decide, or not decide, well, which would help us discuss the decidability. So in this line of thinking, I defined the automata that live on Arolsheim trees. So these are kind of, for computer scientists, these are wild automata. But now, how about automata that live on Suslan trees? They are nicer even, but they have a small problem. They cannot be constructed in ZFC. But they can be constructed using a Morass and a coin reel. So you can think of these automata that live on Suslan tree as being constructed dynamically, because you are constructing the Suslan tree dynamically by knowing a finite piece of the Morass, a finite piece of the coin reel. You keep going, so you look at some limit will be your Suslan tree. So this automaton is going to live in some metaverse, if you want to use a word popular with and totally undefined, popular with our friends in the computer science, applied computer science community like Facebook and so forth. So they all study this word metaverse, which means absolutely nothing, and which goes from science fiction to whatever. But we in set theory actually know what's a metaverse. It's when you study two universes of set theory together. So at least in this kind of context, it seems interesting to study automata that are built in the generic extension dynamically using a Morass and a coin reel, which rather than seeing as a given generic object, we are seeing as the result of a limiting procedure of infinite length. Well, so this is a kind of to finish the talk by some dreams. That's, I think, all I want to say for today. Thank you very much for your attention.
Thank you for a very nice talk.